In the previous video, we saw that for this particular Fermat cubic, given by this equation here, the number of lines on x0 is exactly 27. We counted them by hand, essentially solving concrete equations describing these numbers. And so the next question is, how do we get from this one cubic surface to all possible cubic surfaces? And the idea here is that we can construct an algebraic variety U, which parametrizes all smooth cubic surfaces. In other words, this is an algebraic variety such that every single point in there exactly corresponds to one smooth cubic surface X inside P3. And this is then an example of a moduli space. So a geometric space like a variety whose points exactly correspond to certain geometric objects. And so here is U, and then there's one point corresponding to this Fermat cubic x0. And for any other cubic surface X, you find another point in U corresponding to it. And then the crucial second idea is that we show the function on U, which sends each point to the number of lines on the corresponding cubic surface X, is in fact a locally constant function to the integers. So once you know that, and you know that U is connected, then it automatically follows that this locally constant function must actually be constant everywhere. And so to determine the value of this constant function, we just evaluate it at the single point x0. We find it's 27 there, so it must be 27 at any other point. And then we're done. Then we have counted this number. And this is a very powerful technique in enumerative geometry when you count certain geometric objects. And so how do we get this, this parameter space or this moduli space U? Well, the observation is the cubic surface X inside P3 is uniquely described by its equation, well, almost uniquely. So somehow having a cubic equation means you just take all the monomials of degree 3 in these 4 variables, x0 up to x3, and you take some linear combination. And which exact linear combination you take, well, for this you need to determine what are these coefficients. And to count them, probably by now you have seen this formula already. So somehow if you have a degree 3 equation and you have 3 plus 1 variables, then the number is 3 plus 3 choose 3, which in this case is 20. So you have parameters from A0 up to A19. The reason why I ordered them from A0 up to A19 is that while we care about this equation of the surface, but we only care about it up to scaling, because if you multiply this equation by 17, then you still get the same vanishing locus here. So in fact, we can multiply by any non-zero complex number and still get the same cubic surface. And so what we really care about is kind of this vector of coefficients up to scaling. So we care about an element in some projective space. And we make this precise by saying that the moduli space of cubic equations inside P3 is given by this E3,3, which is just a copy of P19. So somehow the elements of this P19 give you these vectors, these homogeneous vectors of coefficients of this equation up to scaling. And to see a concrete example, the Fermat cubic that we had above, this was described by these third powers of the coordinates themselves. This is a certain element FC in this space of cubic equations, and this corresponds to the coefficient vector C, which just has entries 1 at all the positions corresponding to these monomials. And then, for example, we see here A1, the coefficient of x0 to this 2 times x1, this would be 0. And so it's exactly this vector which has 4 entries, 1 and zeros everywhere else inside this P19. So this element of the moduli space corresponds to this geometric object, the Fermat cubic. And as an exercise, if you like, you can also see what is the moduli space of degree D equations in Pn. Maybe with this discussion, it's not so difficult to guess what it should be. Okay, so we have this moduli space, and moreover, we have another nice object over it, which is called the universal surface. So somehow what we do is we take the space of all possible equations f, and then inside, when you take the product of this with P3 itself, we can look at the points given by an equation f and the point x inside P3, such that x satisfies the equation. So it says that somehow f of x is equal to 0. This is a well-defined point inside here. You can check somehow independent of scaling either f or the point x by some rescaling. So it's a well-defined subset here. And in fact, I mean, you can imagine this is an algebraic equation. So in fact, it's a risky closed subset here. Okay? And we call this this curly x cut out by this equation, we call this the universal family over E33. And the reason is that, well, what happens? So somehow you have here, from this x, you have a projection map which just remembers the first term. So somehow which just remembers this f. And then what is this pi inverse of f? Well, it sits inside, well, this singleton set times P3. So it sits inside a copy of P3. And it's just then the points x inside P3 such that f of x is equal to 0. So in other words, it is just the vanishing locus of this equation f. And so you see why it's called the universal family, because if you take the pre-image of a point in this space of equations, then it's exactly the surface, the hypersurface in P3 cut out by this equation. So you find all of these surfaces in a nice family, and this is called the universal family. Okay, and so this all seems perfectly nice, except now we are really caring about smooth cubic surfaces. And it turns out the space E33 has a lot of elements which are not, in fact, smooth cubic surfaces. Let me just give you some examples here. So for example, one perfectly fine cubic equation is the equation that x0 times x1 times x2 is equal to 0. That's a degree 3 polynomial, it's non-zero. But you see its vanishing locus is just the union of some coordinate hyperplanes. And so this is certainly not a smooth cubic surface because, well, for example, if you're at an intersection point of two of these things, we have seen you can never be a smooth point if you sit in two irreducible components at the same time. And then there's also other points where different things go wrong. For example, you could just take x0 to the power 3. This is a very simple equation of degree 3, but you see its vanishing locus is in fact just a linear hyperplane. And so this is also cut out just by the equation x0 equals to 0. So in fact, the vanishing locus here is a degree 1 hypersurface, not a degree 3. So again, something went wrong here. These things are a bit special, but in general, you can also have an equation like this, which is called the Cayley surface. And it turns out that the vanishing locus of this polynomial here is an irreducible projective variety inside P3. It is a cubic hypersurface, but it's not smooth because in fact it has these kind of 4 singularities shown in the picture. And so again, this is almost good enough, but not quite, because it has these singularities. And so inside E33, there is the locus of such curves or such equations f, whose vanishing locus is not a smooth cubic surface. And we want to throw this out because we only care about the locus u where you get a smooth cubic surface. And to see that this locus that we want to throw out is actually a closed subset of E33, we can apply now the things that we have learned in the last chapter about criteria for smoothness. Because, so somehow, let's look at this big diagram here. So you have here X going to E33, the universal surface over this space here. And then the locus of points f comma x, such that x is a singular point of the vanishing locus of f, we can now describe it explicitly because we have seen this projective Jacobi criterion, and it says that you compute this Jacobian matrix of f at the point x, which is given by these partial derivatives at the point x. And the condition that this is singular at this point is exactly because this one equation is exactly this Jacobian should just vanish. And so you see, you just impose these vanishing conditions here. And again, this is an algebraic condition. You can calculate these partial derivatives and evaluating at this point. This is all algebraic. So in fact, this here is a closed, Zariski closed subvariety inside here. And x also, of course, sits still inside this product here. So the locus where the universal curve is actually, the universal surface here is actually singular. We can describe them. They're a closed subset. And now we use this discussion that we had before, namely we have seen projective space P3 is a complete variety. And so this meant that this projection going from here all the way to just the first vector, this is a closed map. And then this was basically the definition of being complete. And then you see this here sits as a closed subset in X, and X sits as a closed subset here. So if we take the image of this closed set, then it's still closed. So we get a closed subset here. But what is the image? Well, it's just all of the equations f, such that there exists a singular point x inside the vanishing locus of f. So it's just the equations f such that, well, this v of f has a singularity, maybe. And this is closed inside E3, 3. Note that in fact, okay, let me be fully honest here. So somehow here I write f has a singularity because you see, for example, for this equation here, the vanishing locus is just a copy of P2, so it's nice and smooth. But still, I mean, we want to exclude this locus because it's not a cubic surface. And the good thing is this equation here does have a, I mean, somehow if you compute the Jacobian, if you compute the partial derivatives, then they do vanish at these points here. And so somehow we're in good luck here that that in fact this equation of the Jacobian vanishing also excludes these kind of, this is called a triple plane, for example. So some locus here where the equation cutting this out is not reduced. Okay. And so the good thing is this locus that we want to exclude is closed inside here. And so its complement U, which is the full thing minus this locus, is then just exactly the moduli space of smooth cubic surfaces, and it's an open subset in here. In particular, since this E33, which is just a copy of P19, is irreducible, this non-empty open subset, because the Fermat cubic is in U, this non-empty open subset is actually also irreducible, non-empty, and so in particular it's dense. And being irreducible, it's also connected, at least for now it's connected in Zariski topology. And so the intuition behind this is that if we draw U, this moduli space, then we, since it's connected, it means that any cubic surface X can be deformed by some path to the Fermat cubic X0. And this is what we wanted. So Here I gave a bit more detail than Gutmann, because I think modular space are really really nice and cool, and it's a nice application of the Jacobi criterion that we have seen before. So now that we know that the space of all cubic surfaces is connected, the next thing that we need to study is, why is the number of lines on the cubic surface, why is this a locally constant function on this space here? Okay,